Hello everyone. So today we'll go through some application in electric circuits, how to solve electric circuit. We are speaking about linear electric circuits, and it's required to find the current or the voltage as a function of t. And all of these processes are required to be done using Laplace transform. And we can also deduce how Laplace transform is very important in solving these circuits in the S domain rather than the time domain or the t. So let's see. So first, before going to solve a special circuit with some specific numbers, let's go through some basics here in the electric circuits. If we have a circuit like this one, so we can assume we have some current here, and this is the current which is I of t, as a current of t, and we have the source here, and we have this coil or the inductor L, and we have a resistor, and we have a capacitor with some capacitance C. If we have these as numbers, so that's fine. If not, that's okay. We can just using these symbols. So for example here, if we are trying to solve this one, so solving this circuit, it means to find this current or to find the voltage over any one of these elements here in the circuit. Initially, this current, to get it correctly, we can use Kirchhoff voltage law. So it's just only one loop, so we assume we have this source as a function of t. It could be a constant, dc, or anything, or any function in the AC, sine or cosine, or even exponential sum decaying function. And then we have this voltage over this coil, which is L di by dt. This is how to measure the voltage across the coil. And we have a resistor. So this is the first voltage, VL. And we have the voltage across this resistance from Ohm's law. It's just IR. And we have the voltage across the capacitor here. So we have the direct relation like if we have a capacitor, so the current itself, it's C dV by dt. If we need to get this is in the time domain. So if we need to get this voltage as a function of the current, so this V will be equal 1 over C, which is this capacitor, the capacitance of this capacitor. And then instead of this derivative, we will take the integration for I dt. So this will be from some 0 to any time in general t. So this means I can here put this equation as L di by dt plus I times R plus 1 over C integration I dt. This equation, as we previously discussed this briefly, this is some differential equation. And we have here some integral. So this is what's called integral differential equation. It's not that straightforward using the algebra and the regular calculus. So rather we can get this equation as a second order differential equation, or the other way around, you can use Laplace transform. So using Laplace transform, this equation will be this E will be E of S. So I can get this from the table or from any kind of operational properties. And then this L di by dt, it will be L, and di by dt, it will be S times this I minus the initial value of this current. And this I times R, it will be I in the S domain times this constant. And the last part, 1 over C, it's a constant as well. And this integration will be nothing but this I of S divided over S. So all this equation, like we have this differential equation, we have this integral part, all of this equation at the end, it will be some I of S, and here some function of S, equal E of S or another function of S. So at the end, you can get this I, and then I can get this I as a function of t at the end by getting the Laplace inverse of this I of s. And this is how we can see right now the importance of using Laplace transform in solving this electric circuit. So let's see a real example of a real circuit. So let's see. We have here these two loops, and we have a source E, this one, and we have coil L, and we have some resistor and capacitor in parallel, and both of them, this combination, are in series with this coil. And it's required to solve this is the following circuit. Solving this circuit means to find the values of this I1, I2, I3. So first, what I mean here by solving this one, it means find the values of I1 of t, I2 of t, I3 of t. How can we do this one? So initially, we can have loop analysis here. We can use KVL at this loop. So this is loop 1. And we can use also here another KVL, and this is our loop number 2. And then we'll end up with these two equations. This is the equation number 1, and this is the equation number 2. At the moment, it's not required to deduce this equation from the circuit. So these equations right now, both of them are given. So don't worry about how can get this from the electric circuit course, but rather we will have this equation given in the example or even in any problem. So to solve these ones, for sure, something I forgot to mention, we have values for all these parameters. We have the values for this E, a value for this L, and we have R for sure, and we have C. And the most important part, the initial values for these currents, I1 and I2 initially 0. It means I1 at time equals 0 equals 0, I2 at time equals 0, the value of this current is 0. So this is what we mean by this initially 0 for the currents as the initial as an initial condition. So let's see. So the first step, like if we putting down here the steps, first you have to get Laplace transform for these equations given to solve the circuit. 2, after getting this one, you have to simplify this equation or solving this equation to get I1 or I2 as a function of s. And then you will do the inverse Laplace transform to get the function, this current or this voltage, anything given in the differential equation as a function of t. And then all these 3 steps are the same for any kind of circuit. So let's see here. First, we have the first equation, so I will be using this Laplace transform. So this Laplace transform for the first equation, it will be L as I1 as a function of s minus I1 of 0. And the other part, it will be R multiplied by I2 as a function of s equal E as a function of s. The second equation, it will be RC and then multiplied by s I2 of s minus I2 of 0 and then plus I2 of s minus I1 of s. And this equation, the other part equal to 0. So trying to substitute with the numbers here, taking into consideration these values are initially 0, so these values are 0. We can substitute with these numbers. We will end up with the following equation. So I will end up here with I1 times s, I1 as a function of s, multiplied by s, plus 50 I2. It will be equal the 60 over s. and this is equation number 3. And the second equation, which has this RC, it will have minus 200 I1 of S, and then the I2 term, it will have two terms here, so it will have this S and plus 200 multiplied by this I2, and all this equation equal to 0, and this is our equation number 4. So we did nothing. We have this first equation and second equation. We got Laplace transform for both of them, and then substituting with these numbers, which has the value C equal 10 power minus 4, E equal constant 60, so it will be 60 over S in the Laplace transform. We have L equal to 1, and this R equal to 50. After having these two equations, the next step will be to solve this equation and simplifying these equation number 3 and number 4 to get the values of I1 and I2. So here, let's see if we need to get this like solving equation number 3 and 4 to get values for I1 and I2. So simply, we can go step by step here. I can multiply the equation number 3 by S plus 200, and then multiply the equation number 4 by 50 and subtract both of them. We will end up with I1 of S, I2 will be cancelled out, with a term here S squared plus 200S minus 10,000. So this is from the subtraction, and then the 60 over S will be multiplied by S plus 200, and the other equation, which has 0, will do nothing. So this is the equation of I1. So for more simplification, I1 will be equal to the 60 multiplied S plus 200 divided by S over this quadratic equation, which is 102S minus 10,000. This quadratic equation here can be factorized, so this could be written as S plus 100. So, oh, I think I forgot something here. This is plus and this is plus. So the subtraction will give us like this is a positive number. S plus 100 squared. So this what should be at the end. So here we'll end up with this fraction. So this is I1, and then you need to get I2. So I can solve I2 with the same procedure, solving 3 and 4 as well, again. And we'll end up with I2, and you can check this. It will be 60 multiplied by this 200. I'll do the same procedures, but right now 3 will be multiplied, the equation number 3 will be multiplied by 200, and the equation number 4 will be multiplied by S, and then, so just here, so 3 will be multiplied by 200, plus equation number 4 will be multiplied by S. I1 will cancel out, and then we'll end up with just I2. And then we'll have this 200 multiplied by 50, and we have the other terms S squared plus 200S, which will be at the end this 1200. We have this S, and we have S plus 100 squared. So at the end, we have two fractions. These two fractions are considered the I1 and I2 as a function of S. So how we can solve these problems? It's very straightforward. So I1 right now, I can write I1 of S equals sub partial fraction very quickly, s over 100, and another thing s plus 100 squared. Doing this partial fraction, we will end up with, if our substituting was s equal to 0, so this will end up to 100 200 multiplied by 60 over 10,000, so this will be, this value will be 6 over 5, and the other part will be here, this one by substitution is equal minus 100, so this will be 60 plus times 100 divided by this, so 60 multiplied by 100 divided by this 100. So this will have here the 60 here with minus sign. And the other part is s plus 100. We can put this as a and make a common denominator for all of these terms together, and then just substitute with these values and equate the coefficient. We'll end up with this equal minus 6 over 5. Again, we can do the same for I2 of S. So this I2 of S will be equal again something over S plus 100, and another S plus 100 squared. These constant, again, this one by substitution, it will be 6 over 5. And this one, again, substitution very quickly in the whole term, but not in this quadratic equation. So we'll end up with minus 120. And then this one, which is b, again, by equating the coefficient after making this common denominator, you will end up with the value of this b equal minus 6 over 5. After getting these two equations correctly, we can write down right now I1 as a function of t, I2 as a function of t, equal from the table, which is this one is Laplace inverse of I1 of s, and this is also Laplace inverse of I2 of s. This one from the table, 6 over 5, the other part minus 6 over 5, e power minus 100t, the other part here, which is 60, and then this one is t, e power minus 100t. And the last part, it will be 6 over 5 minus 6 over 5 e power minus 100t, and then 120 t e power minus 100t. So this means this is the values for the currents I1, I2. If I need to get I3, so from the KCL, it will be from the equation, this one will be I1 minus I2. So I have both of them, so I can get the value of this I3. So here we can just move quickly after getting this Laplace transform of I1 and I2 as a function of S. We will return back using this inverse Laplace transform. There is nothing new here. We will do this partial fraction. It's a very simple partial fraction problem. And then after getting these constant, we'll end up with this I1 and I2. Something to think about it. For sure, the initial condition, one of the good question, if we are trying to get the initial condition I1 of 0 and I2 of 0, just substitute here. This one will give 0, this one will give 0, so we are with the right answer. But something else to be considered, for example, if we don't know this coefficient very quickly, we can assume this one is A, this one is B, this one is C, and we can get the inverse of this I1 of S as I1 of t in terms of some constant A, B, C, but the function as a time domain function, which the exponential one multiplied by t, or just exponential, or just a constant, it will be the same, but the only difference, these scalars will be still unknown. So if we are having some problem doing this partial fraction and getting these numbers correctly, we can assume this with some coefficient a, b, c, and solve the inverse Laplace transform by giving by giving the final answer in terms of this scalar constant a, b, c. But again, the function, it will be correct. Like this will be a over s, which it will be a. If we have this as b over s of plus 100, this one will be b. And this s plus 100 in the denominator, it will give us in the inverse Laplace transform e power minus 100t. And the other part, again, with this square s plus 100 all squared, this will be t e power minus 100t, but the only difference, instead of this minus 6t as the constant, it's known right now, it could be something equal to c if I can't find this one correctly or in the time limit. So hopefully this one is clear right now. And then let's see another example. So again, in this new circuit, we have here two loops with two inductors, and we can assume that using our knowledge in circuit, we can use this as our first loop, and you get the KVL equation. And instead of having the loop with two coils, I can get this bigger loop, which is our loop 2. And solve this KVL, we can end up with these two equations, equation number 1 and equation number 2. And again, it's not a part of our Laplace transform knowledge right now to solve these circuit equations. So these equations are given, and we will need to use Laplace transform experience right now to solve this one. So we can think about it like the same way we did with the previous example. We can solve using Laplace transform, and then we'll end up with two equations between these parameters, which is here I1 and I2. Sorry, it's I2 and I3, and in the S domain. So just before going through this one, I can substitute with the values here. We have numbers, so we have these values for inductors, we have values for the resistors, and we have a sine function for the source. So here, substituting this into our time domain equation, we'll end up with this di2 by dt plus 11i2 plus 6i3 will be equal 50 sine t, which is, again, this is the same as equation number 1 after substitution. We didn't do Laplace transform yet. The second equation will be di3 by dt plus 6i2 plus 6i3 equal 50 sine t. And this is again our equation number 2 after substitution. Taking both equations right now and doing this Laplace transform, we will end up with the equation again. This is I2 of s minus I2 of 0 plus 11 I2 of s plus 6 I3 of s equal 50. And don't forget, this is a sine, so it will be 1 over s squared plus 1. The last equation, it will be I3 of s minus I3 of 0 plus 6 I2 of s plus 6 I3 of s equal again 50 over s squared plus 1. And we already given that zero initial condition. So zero initial condition for this inductor currents, it means that I2 of 0 and the other one, which I3 of 0, both of them are equal to 0. So these terms are zeros. So here, after solving this equation, assuming this equation number 3 and this is equation number 4, so we can solve this equation together in the S domain. And then we'll end up, after solving, like again, this solving 3 and 4, we'll end up with this interesting equation, which has this I2 of S. I will cancel I3, will equal 50S over S plus 2, and then other one S plus 15, and the other part, which is S squared plus 1. This after doing this factorization for the denominator. Again, we need to do this new factorization here. We'll do this partial fraction. So this I2 of S will be some numerator over S plus 2, another numerator S plus 15, and another numerator S squared plus 1. Substituting with these partial fraction, we can have these values for A, B, C. So this will end up with some constant here. You can check after me. So this 20 over 13. The other one here, it will be this one 375 over 1469. And this one will be 145 over 113 S plus 85 over 113. So that's the new numerator. So this is just 5. Again, after getting these values for the constant, we can assume that already this I2 of t, which is inverse Laplace transform of I2 of S, will be minus 20 over 13 e power minus 2t plus the other constant, which is 375 over 1469 e power minus 15t. These two terms here, we have, after doing this partitioning, we have one of them as cosine. So we have this term, which is 145 over 113 cosine t, and the last term, which is 85 over 113 multiplied by sine t. So this whole term here, this is our I2 of t. So here, what we can do afterwards, just you can check that if I2 of 0 will be equal 0 or not. And it should be equal to 0. The other part, we need to get this I3. So we have two options. Doing whatever we did in the example number 1, like in the S domain, getting the I3 by solving the 3 and 4 in another way, and canceling I2 and getting I3. The other way around from equation number 3, actually, like from 3, we can see that di2 by dt plus, sorry, equation 3 was S domain. The equation number 1 after substitution in the time domain, it was in this form. So it means if I need to get this I3, so it will have this 50 sine t minus 11 I2 minus di2 by dt, and all these terms together divided by 6. We have I2, we can just get the derivative from this formula we already got here, and then we can end up with this I3 of t will be equal, finally, 30 over 13 e power minus 2t plus 250 over 1469 e power minus 15t minus 280 over 113 cosine t plus 810 over 113 sine t. And then this is our I3 of t. Again, our check is I3 of 0 should equal 0 at the end. One quick question. Again, what's the value of I1 of t? It's nothing but I2 of t plus I3 of t. So quickly here, just recap what we did. we have I2 of S. After solving these equation 3 and 4, we'll end up with this partial fraction again. Again, if we don't know these scalars, it's not a big problem. So you can assume this one is A, B, C, S plus D. And then we will end up with I2 of t equals some constant, e bar minus 2t, and another constant b, e bar minus 15t, and a third constant c multiplied by cosine, and the fourth constant and the last one d multiplied by sine t. And we don't know these coefficient yet. But at least we know the function, how this function looks like in the time domain. Again, we need to get the other current, which I3 of t. You can return back and solving 3 and 4 as we did in example number 1. Or the other way around, you can use the equation in the time domain here. It will be like more quick. So here you can use 50 sine t minus 11I2 minus di 2 by dt, which you already obtained it from the first one. And then divide by 6. And we'll end up with I3 like ready in the time domain. And this is what I did here. After doing this, we have I2, I3, and I1, it's nothing but the summation of both branches current. After doing this, I hope it's like do some kind of feeling of the real analysis of the circuit using Laplace transform, and how these circuits can be easily transformed into some algebraic equation instead of having these derivatives or integrals, giving us some hard time solving these circuits. And finally, I would like to thank you for your attention and see you in another one. Thanks.